Please like and subscribe to this channel and press the bell icon to get new video updates.
So the topic I chose was Amazing History of Microelectronics. I think it works very well with the mission of the AWA. So I thought sharing this information will be a great idea to work with you on this. So as you mentioned, I'm from RIT, Electrical and Microelectronic Engineering Department. And so let's get started with today's presentation. I've put forward an outline here, which generally describes about my basic agenda for today's presentation. As I mentioned to you before, it's 100 years of history in 50 minutes, so I'll have to go very fast. So we'll talk about the historic look back, miniaturization of electrical circuits. We call it microcircuitry. That's what we used to call it before. Then transition from vacuum tubes to solid state devices. Then we go to digital age, to computers. And bipolar junction transistors was a big invention, and we went on to Mosfets, and that resulted into monolithic integrated circuits. We'll talk about that. And now we are into scaling era. We are scaling these devices so much that we are building more and more on the same platform to get to the computation level that we have as of today. While we were doing all this on discrete components, monolithic integration, we also had to work on better and better printed circuit boards. So printed circuit boards also went through miniaturization. And then I will talk a little bit about memory and then look to the future. So this is what my outline is. So let's get to start it. Now, it's very interesting that my experience, as you mentioned, I did my education in India. I was a undergraduate student. At that time, the only device we had in our home was a Murphy radio, a vacuum tube radio. That was our link to communications and music. And so it was really interesting that we have this iconic advertisement, we call it Murphy Boy. And that advertisement appeared on every commercial in every newspaper. So people bought a lot of Murphy radios. So I used to listen to the radio all the time, look at the vacuum tubes inside. And then when man landed on the moon in July 1969, we were all surrounding this radio, me and all our friends and family, and we listened to the very famous quote from Neil Armstrong that the eagle has landed. So we heard that on the radio. And it's so interesting that this information came from Voice of America. Voice of America had built a communication network for the rest of the world to get information. So we got it on the Voice of America channel on this radio. And when I visited AWA, I was so happy to see the studio of Voice of America because it brought me the old memories of listening to VOA on our radio. And interestingly, in this chip, the integrated circuit that went on the moon was the first monolithic integrated circuit that went in space. And that was a bipolar-based chip. And interestingly, I got that chip, and now we are actually testing it in our lab. So I'll share you some of the information that we have on this amazing microchip that went on the moon. So that's why it sort of covers the two things together, from tubes to integrated circuits, and through Voice of America. So that's what I was very happy when I visited AWA. So let's say, look at back to the history. So Thomas Alva Edison, he discovered the light bulb, which actually illuminated the whole world. A vacuum tube, a vacuum which has a filament which gets hot, it emits electrons, gets hot, so light comes out. It's in inert ambient so that the filament doesn't burn out. And that was the beginning of the light age. So with that, then we come to Sir John Ambrose Fleming, who actually used this concept to build an active device. Is called the vacuum diode, and then later on the vacuum triode. So that gave us the beginning of active devices that we can use for communications at the time. Then, of course, we have Marconi and Heinrich, we just see it, Rudolph, and they took this technology of vacuum tubes to build the radios I was just talking to you about. So that was a very, very good beginning of that era of our world. So from vacuum tubes to light to radios, that was big innovation. So now we talk about electrical circuits. Basically, electrical circuits are architect of the flow of electrons or flow of the current. So we want the current to flow where we want it to flow, and we don't want it to flow where we don't want it to flow. So we use metals and insulators. Based on that, we can build different types of devices, passive components like resistor, capacitors, and inductors. You see here discrete resistor, discrete capacitors. So these perform certain functionality in your circuit, but in order to have a real computation and judgment, we need active elements like 2-terminal devices or 3-terminal devices. 2-terminal devices are diodes. They act as rectifiers, and we can use them to convert from AC to DC, and we can use them as rectifiers. 3-terminal device, you have additional another terminal, like for example, in this vacuum tube, if you put another control grid here, then you have this terminal which controls the flow of the current in the outer terminal. So you can actually make an amplifier or you can make a switch. So that was so when we combine all these, we form the electrical circuits. So vacuum tubes to active devices came through this innovation I just mentioned. If you take this vacuum tube, you just have 2 electrodes, cathode and anode. When you apply a positive voltage here, current flows. Negative, it does not. So it acts as a rectifier as shown in this IV curve. And when you put a control grid, then you have emitter, base, and collector kind of behavior. So by controlling this grid, you have 2 different voltages here. So when you control these, you can amplify the signal here by a little change in this particular voltage, and you get a lot of gain in amplification. So by changing a little bit of base current, you have very good gain in the current flowing through the collector. So that gives us a 3-terminal device, which acts as a amplifier or as a switch. So when you combine all of them, so this is the route which I'll be talking about today. You have these discrete components. They have some functionality. Resistor, your voltage is proportional to the current, and that's Ohm's law. And we can control the amount of current that flows through a resistor. Capacitor, 2 plates separated by dielectric. Normally DC current does not flow, but when you change the current, when you change the voltage a little bit, the current flows. An inductor, the other way around, it's a coil of wire. So only when there's a change in current, you induce a voltage. With these functionalities, you can build a lot of circuits. But we need active devices like diode and triodes. And in order to make the circuits, we use to conduct electricity using metals. We use insulator to stop the electricity flow. But semiconductors are the material which brought us to the solid state era. Because here I can control the semiconductor conductivity, and I can get another functionality. I can produce junctions, and they respond to light, they respond to temperature, they respond to even other mechanical pressures and things like that. You can make lots of devices out of semiconductors. How do you build them together? We can make a resistor in a semiconductor. We can make capacitors. We can make inductors. So this way we can go from vacuum tube to discrete components to integrate circuits. So that's the journey I'll be talking to you about. So towards microcircuitry, initially in olden times, people never used the word microelectronics. They use microcircuitry, So in order to put all these components on one platform at that time, they started building printed circuit boards. So 1850 to 1900 was the spread of the electrical power. So for telephones, light bulbs, and consumer cameras, so they wanted to use more of these components. So therefore, this patent was filed for the printed circuit board. So in 1900 to 1950, German inventor Albert Hansen, he filed first patent on a PCB-like device, which was used for telephone system. It had a flat conductor on a multi-layer insulating board. Then later on, Charles Dukas, he printed wires onto a board with a conductive ink. So you can put a conductive metal ink, you place where you want to on an insulated surface. Later on, they went on to electroplating. 41, we started putting copper foil on a non-conductive glass base. And then you can do multi-layers of the foils. And then it was first included in the radio made by Paul Eisler that used the first printed circuit board at that time. So you started now putting more components on a small frame of platform. In mid-1900s, the first significant post-war use of PCB came in 1947 from Bell Lab transistors. I'll talk about that later. In 65, the Army patented processing of assembling electric circuits. So they started building this PC board. Now let's look at this picture here. This is an old Motorola television. From the back side, you see how the circuits are wired. So how messy it is. So that's why there was a big need for very nice printed circuit boards, especially for space applications. We wanted lightweight boards. So this was the PCB for space, and this was the PCB from 1970. So this had a through-hole technology. They drilled the holes and they connected through the wires from one side to the other side. So that was a big change in the PC board technology. So here on the left, I explain the PC board process flow. If you go through it, basically you are plating and you're etching and you are inspecting, you use certain mask. It's very similar to photolithography that we use for patterning in integrated circuits now. So this shows you the PCB comparison of the old times to what we have today's motherboards. So they are very dense, they are very nicely arranged, and they have sockets for putting different components on the board. So that was the 1970s. This is of today, and some of these PC boards look like this. So if you see very carefully the PC board I have in my hand, and it's very interesting that how dense wires they put and how they put those bulbs and sort of the drill holes and put the solder bulbs there, and how it is able to solder to the connections, and you're also able to put your chips on the sockets. So all the bond pairs are aligned properly. So that's quite a good technology that helps us to put these components. So that was called the microcircuitry in those days. So then we moved on to the digital computer and digital circuit design theory. Way back in mid 1800s, George Boole, he discovered the Boolean algebra concept. So that concept was based on binary logic, 0 or 1. With that, you can make so many gates and or NOR gates. So they provide a certain computational for us, how much you put on signal A, how much signal B, what's your output. Based on that, you can convert all your calculation into a binary logic circuits, logic theory, and then you can build some switches which turn on and off, and you can do the computation. And then von Neumann architecture used this arithmetic unit and logic unit together with the control unit, and it had some memory register along with it. It started using some of the concepts learned from computations using Boolean algebra. But more importantly, Elwood Shannon, he brought the Boolean logic to analyze behavior and optimize design of relay circuits. So the relay circuits were using 0 or 1 on or off switches. And then John Athstorff, he discovered the idea of combining electronics with binary arithmetic and Boolean algebra to build electronic digital computers. So that was a big step forward. And he was using the switching relay circuitry for machine logic and electrical and electronic components. So that was the beginning of using binary logic switches on and off to do serious computations. If you look at the history of mankind, calculations has always been a very important aspect of human life. How much food we have, how far do we have to go? So computation was so important. 3000 BC, it was invented by abacus. It's invented by Chinese. It performed addition, subtraction, and division using these beads and columns. Then slide rules were discovered. Finally, mechanical calculators, which were basically mechanical wheels, and you could turn them around with certain RPM for different levels. So you can do the computation at every level, 1, 10, or 100. And that was a good thing to start doing some calculations much more faster than some of these devices. Then 1832, Babbage difference engine was made. That was one of the most, I would say that, highly impressive device that can do calculation by these mechanical moving parts. So I'll show you a slide on that. In 1931, we went to differential analyzer. And that was discovered by Vannevar Bush in 1931. The machine could solve regular arithmetic, but also do differential equations. So that was a big put forward. 1804, Jacquard loom, invented by Joseph Marie Jacquard. It could use the punch card to produce a certain pattern here. So we could print certain patterns by using punch cards. Then Herman Holith tabulator in 1881, that brought a punch card system to do serious calculation like analyzing 1890 US Census data. So when you have large data to compute, to store, so this is something that was helping a lot at the time. And that became part of what is now IBM, the International Business Machine Company. Then IBM made an accounting machine. It used punch card and tabular machine in 1949, and that was called IBM 407. So that was beginning of these computation machines using the punch card technology. So this is a schematic of the Babbage difference engine. You see here how involved it is. It includes so many of the gear, wheels, rods, ratchets, pinions. So they spin around. You can set up your calculations based on what's the each and all rotor is marked in terms of the scale of numbers. And then you can do computations like adding, subtraction, and serious calculations. It took 6 years to build, had 2,500 parts. At that time, it cost about 17,500 euros. So it was a big machine at that time. So there is very good display at a reference at the bottom left, a Babbage engine that you can see actual visual display of how this engine works. So that was a big push forward in doing very strong detailed calculations. Then relays to vacuum tubes. So most of these punch cards, before punch card, we use relays. They use actually mechanical switches, something like that. You have electromagnet and you have on-off switches. So something moves here. It has moving parts. You can turn on and off depending upon the current that flows to the magnet. And those are electromechanical, or call them electromagnetic switches. So later the relays were used in telegraph systems. So we know there are Morse code used to be sent with these relays. So the first digital programmable computing device, logic circuit relay on vacuum tubes, was then made, because now vacuum tubes can do 0-1 logic on or off. So therefore it resulted into a big computer, ENIAC, and then Alan Turnic's Pilot Ace computer. So here we are using basically, instead of these mechanical switches, electromagnetic switches, we are using the vacuum tube. So this is a picture of an electronic numerical integrator and computer we call ENIAC, very famous computer of its time. You see how big it was. It was using vacuum tubes. So look at how many vacuum tubes are placed here. So that was a very, very big achievement of those time. And it was built by John Markley and Presper Eckert, who was circuit engineer in the Moore School of Electrical Engineering at University of Pennsylvania. So that was built in 1952. So ENIAC computer became the workhorse of computing at that time. Now, vacuum tubes in the first computer, as I mentioned to you, it had 17,500 electronic vacuum tubes and weighed more than 60,000 pounds. Very heavy machine. It could perform 5,000 additions and 300 multiplications per second. It was very fast at that time, but slow from today's standards. But at that time, a very fast machine, and was 1,000 times faster than existing machines at that time. And as I see here, when I read about this computer, I talk about hidden figures. The 6 women contributed to the success of this computer. Their names are listed here: Frances Villas, John Jennings, Ruth Leiterman, Kay McNulty, Betty Snyder, and Marilyn Westcott. Hats off to them that they did so much programming, they say, that unknown to many, these 6 women wrote and tested the programs for ENIAC. They say without their work, it may not have been possible to complete. So that's why I call them hidden figures. So they did a great job. Now, we replaced relays, mechanical relays, with vacuum tubes. We still find vacuum tubes bulky. Can we look at something else? So replacing vacuum tubes, that was the beginning of the solid state electronics. 1874, that was a big invention by Ferdinand Braun, who found that when he dipped a metal wire in lead sulfide and found that current flowed only in one direction. So only when you apply a forward bias, current was flowing, otherwise no. So this was the first invention of metal semiconductor contact, which was a rectifier. So that was a big deal. And later on, it was used in 1901 in cat's whisker detector. So Jagdish Chandra Bose, professor in physics in Calcutta, India, he demonstrated that this lead sulfide crystal could be used with a metal wire to detect millimeter electromagnetic waves. So that was the first demonstration of picking up electromagnetic waves using a metal semiconductor contact. So that was beginning of the solid state. Then later on, a copper oxide rectifier was built. It converted AC to DC power. it was purely solid state based on the metal and semiconductor, metal and solids connections at that time. So that was the beginning. At that time in 1930s, I think this was a very big invention in 1930 by Lilienfeld. He filed a patent for something called a field effect transistor. At that time, he called it MESFET. So what he showed that if you have a material like solid, you connect from A side to B side and current flows through it. But if you put another electrode on the top and you apply some electric field here, you modulate the current. So he demonstrated two gold spots here. This is a copper sulfide here, and there is a aluminum gate. So when you apply the voltage to the aluminum, you change the current flow between source and the drain, we call it now. So that was a very big invention, but this device could not be built because of excessive interface charge. So this device was normally on, you could only turn it off. But it was not normally off that you can turn it on. So that's why it stayed for some time in research, but people were always looking for this device to make. So that was, but it's called one of the most innovative patents in semiconductor history. Then came the discovery of PN junction. 1940, Russell O discovered the PN junction and showed the photovoltaic effect in silicon. So what he showed was, if you have a silicon bar here, if you change the polarity from N to P type, something like P to N here, it forms a junction. And he showed that this junction acts like a rectifier. And when you shine light on it, it develops photovoltage. So that was called the photovoltaic effect. That is the fundamental principle behind solar cell. So he wrote in his notebook here that how this particular this device works. And he explains very nicely, if you read carefully, that it has some depletion width. When you shine the light on it, it creates electrons which flow through it. So that was the first invention of PN junction. It acts like a diode and also acts like a solar cell. Based on that now, John Bardeen, Britain, and they constructed a first junction, a point contact transistor. So this is the actual picture of the device here. So it has a basically plastic wedge in a triangular shape. The gold foil on two sides. There's a small gap here. And it sits on a P-type layer on an N-type germanium layer. So this is a cross-section of this device here. So this device exhibited a transistor behavior. So you have here emitter and base and collector. So by applying a voltage here and here, this is forward bias, this is reverse bias, you can actually show that it acts like a transistor. So that was a big invention. And later on, they got the Nobel Prize in 1956. So that was a beginning of a solid state 3-terminal device, which is a transistor. But it was a point contact device. So you put a point contact here and a here. And there is a junction here, but it was later on improved to a PNP or NPN device, and that is called the junction transistor. But point contact transistor was considered as a big victory, and RCA began developing its own point contact transistors in 1948. These are some of the pictures of the point contact transistor made by RCA, and some of these TA153, 165 are used in building the first television made up of point contact transistors. So this is from this IEEE spectrum reference. I read the history, and this particular television was made using point contact transistor for the first time. Then from point contact transistors, we went to junction transistor when we actually could build an NPN device like that. So this is a germanium bar. It's N-type on this side and N-type on this side and P in the middle. So NPN. And this was the discovery of the junction transistor. Here you see Shockley describing the band structure of this device. So this device was much more stable than the point contact device. So therefore, most of the production of point contact transistor moved on to the junction transistor. So that was the revolutionary change at that time. So this was a big discovery, big news on New York Times in July 1948. The news of the radio, a device called transistor. So the word transistor was invented because transfer of resistance, they call it transistor. So here you see John Bardeen, William Shockley, and Albright at Bell Labs. This is their patent, and this is a cross-section of the device. So in this cross-section, you see it's slightly different from point contact because now you have NPN. So this is your emitter base, and this is your base collector, and you can bias in different directions to make it turn on or off, or even amplify the signal at the collector. So that was the solid-state transistor. So this is a picture of the 3 types of devices at that time. So the person holding is from AT&T archives. So here on the palm, you see from left a phototransistor, a junction transistor, and a point contact transistor. This is the actual picture of the point contact transistor. The 2 leads are shown here. The 3rd lead is over there. And this shows you a production line of the point contact transistor by Western Electric. So they were building type 2 point contact transistors in this production line. But later on, they moved from point contact to junction transistors by 1960. So this particular, they started making more of these devices in 1960. So therefore, we celebrate in 2022 to 2023, IEEE decided to celebrate 75 years of the anniversary of the transistor. It's a very revolutionary discovery. So Electron Device Society has a magazine. They gave the very nice article on that. And I put they gave me a banner from IEEE, and I put the banner in AWA Museum. So it's putting here. You see here, visitors are looking at the first transistor radio here. And here I'm standing with my student and with Steve and the staff member from AWA. So it's really a good exhibit. So IEEE was very happy that I placed the banner over there. So that's tells people about the sort of importance of this discovery of transistor. So then transistorized consumer product started. So first transistor radio, handheld, lightweight radio, something like this, you know, they were so popular, people used to carry them in their pockets. And so Sonotone 1010 hearing aids, this shows here, and these are TR1 old transistor radios. And Manchester TC Computer, they built first transistorized computer. So this computer doesn't have vacuum tubes. It's built with all transistor radios. So that was 48-bit machine, used 92 point contact transistor and 550 diodes, and fabricated by STC. That was in 1955. Now, while we are doing all this, we have to make these things, therefore some processes were developed. 51, development of zone refining. How you can take a crystal length and zone refine it so that it becomes more purified in order to make a high quality device. So zone refining, William Fan and Henry Thor developed this technique. They did ultra pure germanium, and later on it was, of course, used for silicon. Then diffusion process was developed to introduce impurities, make it P-type or N-type. How do we diffuse? So they actually made some process, thermal diffusion. Then development of oxide masking. If you use silicon, you grow oxide, or then oxide acts as a mask. So you can pattern the oxide, like here they show, they pattern the oxide to write the end here, using a contact lithography, something like that, a stencil-based lithography using ruby lith. So this was a contact lithography. That means you make a stencil of the pattern, you shine the light on photosensitive film and expose it and etch oxide. So this way you can pattern this. So that was the beginning of photolithography technique and to make silicon devices. Transitioning to silicon then, but of course, germanium had some problem. Germanium is a small band gap semiconductor. It has more off current. Also, its temperature variation is very sensitive to temperature after 70 degrees C, especially for space applications and hard radiation application. You would want silicon. So therefore, they tried making silicon transistors. So this is Texas Instrument first silicon transistor here, shown here. Look at its size compared to the stamp. So it was a very small device built with silicon NPN transistor. So then they use this for making a more grown silicon and making more devices. So this became into large scale production because it was big progress of making silicon-based transistors. So now we have transistors, we have resistors, capacitors, we can make circuits, we can put them on printed circuit board. But can we put them all together? That was the concept, that first all semiconductor solid circuit. That concept was put forward by Jack Kilby in September 1958 of Texas Instrument. he said, can we put NPN transistor and some other capacitor and resistor on the same substrate? So that's what he tried. On the right, very famous drawing here, it shows the first device made by Kilby. It is a germanium bar. The portion of it acts as a resistor, and the transistor is right here. And metal wires are flying wires. They go and connect to the terminals. But the metal wires were not yet part of the circuit, but they were connecting like this, as shown here, a flying wire like this. So these are resistances. There's a capacitor here, and there's a transistor here. So that was considered to be the first transistor, which actually accommodated transistor, resistors, and capacitors. So that was called solid state circuit. Now, can we make it better? Can we put the wires onto the substrate? And that we'll show you later. Now, I give special tribute to Jack Kilby. He passed away in 2005, but we were so proud that he came to RIT and he inaugurated the nation's first program in microelectronic engineering. And here you see him standing in RIT with our dean at that time. So he was honored with so many medals and so many inventions and patents, and RIT honored him with PhD degree, honorary degree. And he gave us this wafer, Texas Instrument wafer, signed by him. He gifted us to RIT, and this is a precious thing we have here to show. So this shows his signature on this wafer here. So we are very proud of that. So then came the first planar integrated circuit. In 1959, monolithic integrated circuit concept was patented. This shows you the patent. Actually, it produced these transistors, NPN transistors here, shown here, and with metal wires. So in this structure, this 1961 monolithic IC, you see transistors are here, 4 of them, 1, 2, 3, 4. These 2 resistors, these are resistors. They're diffuse resistors, and these are metal lines. They're integrated onto the chip. So this was first monolithic. No flying wires. The wires are printed onto the chip. So that was a big achievement at that time, first integrated circuit. Then it came to logic chips now. So if we can replace this big vacuum tube by this small transistor, which shows here on the right, this diagram. This is the transistor, which is this one. And now you can package up onto your logic chips, and they can go to your computers here. So that was beginning of 2 triple input NOR gate chip. This was shown here. And it used resistor, transistor logic, resistors and transistors. So they started building those, and that come to the circuits. So where did they go? Sorry. So early integrated circuits, NASA Apollo guidance computer was the first ever to use the integrated circuit built at the time. So here I'll show you Apollo guidance computer chip later on. This is the chip that was built. It's a dual 2-input NOR gate, 3-input NOR gate. And this particular chip was given to us, and with the courtesy of Jimmy Luckey, I'll introduce you to him. And he connected us with Eldon Hall, and we got connected to the daughter of Eldon Hall, is Pamela Hall. She lives in Florida. So we spoke with her. They gifted us some computer chips that we delineated and we're studying in our own lab. And I'll show you that in the next few slides. So this particular chip went on the moon, and it was the hardware designed by Eldon Hall, which I'll show you in the next slides. So it was fairly light compared to other computers at that time. It weighed 70 pounds and was about 2 feet long and 1 feet wide, 6-inch thick. So it was mounted on the wall of the spacecraft. I can show you some pictures in the next slide. So here you see Buzz Aldrin sitting in lunar module. So that's where the computer is sitting here. And this is the block diagram of this command module computer. And Eldon Hall from the Drake laboratory, and he designed these computers, tested it here, and they were tested under radiation hard condition, under vibrations, and then certified to go on the Apollo program. So we celebrated Eldon Hall. Unfortunately, he passed away in May of 2022. So we celebrated his contributions. We honored him in our Imagine RIT festival last year. And there we showed that the chip that went on the moon is shown here. We X-rayed the chip. This is the dimension of the chip. We made a layout. And the students are demonstrating to the public that how this chip was functioning. And the chip was provided by Jimmy Luckey here, his picture here. He's ex-NASA technician. He's founder of spacecomputer.org organization. and he gave us this chip and he connected us. So I am thankful to him for that. And we continue to work together in this particular, that innovation that my students are very much interested in. So we are doing this project, and it's supported by IEEE because it's a very good educational kit that we can develop for students in the future, building these chips using layouts in our lab. So this computer chip, actually, the command module had either block 1 or block 2. Block 1 was 3-input NOR gate. Block 2 was dual 3-input NOR gate. So this is just single one. You see, it looks like that. So we brought it to our lab. We took the microscope picture. We measured the dimensions. What's the size of each and every layer here? We measured that, and we take the chip in our lab. We tested it. It gives the right kind of IV curves. So it's still functioning very well. This is the cross-section of the circuit. These are the dimensions. Now, looking at this dimension, 25 micron and all, let's relate these dimensions to our perspective. So 1 micron, 10 micron, we are in micro world right here. So human hair is about 70 to 100 micron, this human hair. Red blood cells about 8 micron. So we are building devices in this range right now, and we are soon moving to the nano world. So this is actual chip. We measured every dimension. This is the chip that went on the moon. So you see, had dual 3-input NOR gate, and this is chip, package chip. This opened, and then this measured, and then this is the process that went into it. So we are basically building this one right now. Now this was BJT. Now bipolar junction transistors do consume more power, and they also take more space. So therefore, we were looking for lighter devices. And based on the field effect device, that metal oxide semiconductor transistor was built in 1960 by John Atala and Duan Kong at Bell Labs. So whatever that Lilienfeld proposed, it was built now, many years later. How? We make N-type layer and N-type layer here with the gate oxide here, and we have 3 terminals. You can turn it on and off, applying the voltage to the gate. You can make N-type or P-type. So that was the beginning of the MOS transistor called MOSFET. You hear the top view? This is called source. This is called drain. This is your gate. So this device can be turned on and off by applying voltage to the gate. So that was a big thing. It was small. It was consuming less power. We can condense more on a circuit. And this was in 64. First commercial MOS transistor was built by MOS IC. Here is called General Microelectronics. So this is a first PMOS-based commercial MOS integrated circuit. It was used in a Victor comptometer, first calculator. And here is a picture of Andy Grove, Bruce Steele, and Ed Snow discuss the MOS physics of the MOS transistors. So that was the beginning of using MOS transistors on actual devices. So this used PMOS device, something like that, and built this custom MOS chip for built. So the beginning of the integrated circuits now. So I'm here right now in this here. So MOSFET 1960, integrated circuit by Kilby. Then CMOS was, if you fix the MOS transistors together, PMOS and NMOS together, it's NMOS and PMOS. When you couple them together, you can make more circuits, which are gates like inverters and NAND gates much more condensely. So therefore, CMOS was picking up now, because either this device is on or this device is on. This way you can make them logic gates. So that was beginning of the CMOS. So we started with bipolar, went to PMOS, went to NMOS, then went to CMOS, that means N, P together. Then we can combine bipolar and CMOS to make bi-CMOS also for some power applications. And now integrated circuits can be classified into this fashion. They're microprocessors, memory, or application specific. That was beginning of now microprocessors. How chips are made? Just a quick look at the chip making. You will start from sand. We make pure crystal. We grow crystal of silicon, pure silicon, then grow crystal, cut the wafers. These are the wafers. And then you start printing your chips using photolithography. You keep doing layer by layer by layer, introduce dopant where you want. And once all is done, you make so many dies on the wafer. Then you cut them. Each die is a chip that goes on the package, connects to the bond pads, goes to circuit board, and that's where your electronics is. All these chips are made in foundries or in clean rooms. because these are so small, features are so small, we don't want contamination. That's why people wear bunny suits and the air is very clean in the modern fabs. Because each dimension is so small, you can't afford any contamination. In olden times, these devices masks were made for different layers manually. They were designed manually like that in olden times. You imagine now hundreds of devices you are building layer by drawings, but later on, new CAD developed. Computer-aided design tool developed. Now everything is done on computer using libraries, and masks are made, written on quartz plates. And this is world's first microprocessor built by Intel in the Intel 4004 in 1970s. This is schematic, this actual view. Look at how dense these circuits are here. It was built with 10 micron design rule at that time. So that was first microprocessor. I remember the commercial Intel inside. So that was a big thing at that time. Then Moore's law came along. Okay, in 1965, Gordon Moore says, now we can make so many devices, we'll cram more and more and more. So number of transistors will double every 18 months. So we kept in from 1970 to 2020 to even now 2024, we are putting more and more transistor per chip. So we're getting denser and denser. So that's famously Moore's law. So this is 1974 Intel 8080, Intel 86. So we went from 5,000 to 29,000 transistors. Went to Intel 386 with 275,000 transistors. Then AMD came up with 200,000 transistors using 386 microprocessor. So there was now competition, AMD and Intel. And we have now here Motorola built another microprocessor. And then Intel came to Pentium processor in 1993 with 3.1 million transistors. You see that how dense the structures are of each devices in this? That's amazing. That's IBM introduced PowerPC in 601 with 2.8 million transistors. Then Intel came with 42 million transistors. Very dense way. This is Intel iCore. This is a new generation of Intel processors. They have multi-core and iCore 7, iCore 9. So they continuously are improving more functionality and more density, more computational content in them. This is the comparison of Intel 86 in 78 to Intel iCore in 2017. It went from 4-inch diameter silicon wafers to 12-inch diameter silicon wafers. And also it went to from the size, it went from 10 micron to 14 nanometer technology node at that time. So making billions of transistors per. So this is how Intel 14 nanometer transistor looks like cross section. If you cut the chip and see the cross section, you see how many multi-levels of metals, and the transistor right sitting there here. So transistors are right at the bottom. They follow the 14 nanometer rule, and then metal 1, metal 2, metal 3. There's so many metal layers on top, and you see that metals are mostly copper, dielectric, constantly placed. And that was a very, very dense chip in 2017 made. Now Intel is giving a roadmap to go to angstrom era. So we keep on shrinking the devices, keep on making more and more and more functionality. Now let me give you a comparison here. If you think of Manhattan, let's say you aerial view of New York City. If you take New York City and condense into just 1 inch square, the modern chip is more denser than the New York City. Just imagine that. So many homes, roads, pipes, electrical lines, and it has much more than that. So this tells you how dense the circuits are. And then because it became a big technology, so TSMC Foundry was founded by Morris Chang. That was a big step forward. In 1987, he founded this foundry business. That means you give your design, we'll make for you, because making is so complicated. So now it has 12-inch semiconductor fab, which makes so many foundries. It has 65% of the market share of making chips. It has technology roadmap. It will go from 1996 to 2025. It will go to about 2 nanometer era. So right now, top foundries are TSMC #1, Samsung, Global Foundries, and Intel Foundry Services here. So most of these are the foundry businesses that are very promising right now, and they are building the chips. This is how a typical foundry looks like. It's highly automated. You have FOUPs here. Wafers move around from one bay to another bay. They go through all kinds of deposition, etching, deposition, very automated. You see very few human beings here. And the equipments are very, very sophisticated. This just on March 15, 2024, it was announced that 4 trillion transistor is announced by Kebras. It uses the TSMC 5 nanometer process. So this is the progress in that. So we see that from mechanical computing took 5,000 years from abacus to differential analyzer, Jacquard loom to punch card, which used that to IBM accounting machine, took 150 years. Light bulb to vacuum tube, 63 years. We make ENIAC computer. Junction transistor to integrate circuits took 14 years. And first IC was made. And microprocessor from 1971 have gone from 10 micron to 5 nanometer in 53 years, the multi-core. So the rate of innovation increases exponentially with time as technology matures more rapidly. We've seen that happening. Now on memory side, I talk about computation, but on memory side, we use punch card, we use tapes, and we drill holes wherever you want to store the memory. We went to Tinker tapes to magnetic tapes. IBM pioneered on that. Magnetic material, you can do that. So that's what started with the magnetic core memory. You use these magnets, which are toroids, and you have bit line and word line going through it. So if you send a message to this particular toroid and switch the magnetization, north to south, south to north, and then that stores the memory, and you can read it from the sense wire. So that became the core memory at that time, and that was used in Apollo program. So Apollo guidance computer used the ferrite core memory. This shows the actual picture of the memory bar here. You have all these, so they were actually personally weaved by people with hands. So they were woven with those wires going through them. And it was used to store the memory and retrieve the memory. It was non-volatile memory because once you store it, if power is gone, it still maintains the memory. That's why it was used as a non-volatile memory. But it occupied more space because toroids are not very small. Then we went to semiconductor memory. So DRAM was invented by IBM. DRAM is a capacitor-based memory that you charge a capacitor and you store the information. But when you turn the light off, when you turn the electricity off, the charge leaks. So therefore, it's a volatile memory. It stores as long as power is on. But it was very dense. So it started working as a solid-state memory next to your computer. So you didn't have to use ferrite memory core for that. So that was the beginning of the static random access memory or dynamic random access memory, and it became the mainframe memory in computers. So there's some timeline, but most important timeline is this one. In 1978, Micron was founded in a small office in the basement of a dentist office in Boise, Idaho. So that was the beginning of one of the largest the largest memory company we have, Micron. It was founded in 1978. They started working on DRAM, the dynamic random access memory. So that was a big step forward. At the same time, we were working on more and more dense memory, but we also have to store memory. That storage class memory wants magnetic tape, ferrite core, then came hard drives, music tapes. We went to DRAM, then bubble memory was also magnetic memory, floppy disk, 8-inch floppy, 5.25 floppy, and those were all magnetic based. And then we went to CDs. CDs were basically phase change memory. They stored the information when you change the material properties, and they were used for music mainly or for movies or images. But we wanted to look for solid state memory, so we used USB and SD cards. So we want to shrink them, make them lighter, make them faster. So we went to other sources of memory. The hard drive was so built by IBM, it used a big airplane to carry it. It was so big initially that stores most of the information, but now it becomes so small. So from 1956 to 2005, it went from 2000 bits per square inch to now it's going to 1 terabit per square inch. The hard drives have become so good. So it's a picture of a modern hard drive. It is a right head of a magnet and a read head. It magnetizes your material north and south, either laterally or vertically, then reads it. So it's almost like this head lands on the magnetic material at 1 nanometer spacing, something like A Boeing 747 is landing on the Earth with 1.5 millimeter gap. It goes so close. So that's amazing technology, that how it does it. It's still used, key players are Toshiba, Western Digital, Seagate. It's still being used as a storage class memory. It's used in data centers and used for archival memory. But we want to go to solid state memory, which was discovered by Fujito Masuka, flash memory. Flash memory stores information by trapping electrons. So SunDisk, this is how it started coming. So this USB is called Universal Serial Bus. It's a flash memory, and it can connect to any device. And now you compare hard drive with solid state device, you see the difference between the two. So both are basically have niche market in storage class memory. We are using archival data, or we're using the current data on your computer. So flash memory became big since 1984. Flash memory is built by a chain of transistors, vertical chain of transistor. They're about 232 story tall. This is the transistor, and this shows you how flash memory has gone from telephones to personal digital. So they are gone from cloud computing to gaming to wearable healthcare to industrial automation, security, every place. So this is the evolution of the flash memory to such a long era of such a range of devices that we can't imagine. So this has become a very much a great technology, but it's also approaching some limits. We'll have to look for new solutions. Now, the wafers are becoming bigger and bigger. Now the devices are being made on 300 millimeter wafer. Bigger the wafers are, the more devices you can build. And therefore the crystal puller, which pull the crystals, are becoming bigger and bigger, taller. So this is a crystal puller in Rochester, New York, a company called Linton Technology. They actually design crystal pullers. So this is shown one of that, and this silicon is melted here. This is the molten silicon at 14, 17 degrees Celsius. We put a seed and grow a crystal. So this, you insert a seed, this crucible, you pull a crystal, this is a crystal. This looks like that. This is a crystal, ingot, you call it. These are my students. I take them for a field trip, actually show them this tool. So maybe you should take a visit to this facility. It's in our backyard here. So they make crystal pullers. In Micro E program, RIT started in 1982. So we started a clean room for education. We've been building all kinds of devices with students inside the clean room. We started with BS program, master's program, and PhD program. And most of the processes we develop with the help of students and give them the design projects. So that's why RIT is very much passionate about semiconductors. If you look at the Bell Labs, I got these archives from the Bell Labs. Bell Labs from 1920 to 1970s and 80s, phones, space, internet, music, cell phones, radio, television. So all these innovations came from Bell Labs, which is very amazing. We need more Bell Labs here. So that was a very, very amazing discovery by them. In the future now, of course, I talk about history, but in the future, we are seeing that the devices will start becoming more and more smaller and smaller, taller and taller, and new materials will come up, and therefore we'll bring a new combination of materials and device structures so that we can make them smaller and faster and more energy efficient. So it's a very big field. That's what we'll talk about in the future. So let me show you that. A small question from a 2-year-old. Let's ask her. Alora, can you name 3 terminals in a FinFET? Good. See, this is what we need to do. We need to teach young kids early on. And she's holding a 3D printed FinFET in her hand. And she's asking me, what is this? I said, this is a FinFET. And this is source, gate, and drain. And she knows that. So we need to teach kids. Thank you. Okay, so I'll conclude with my acknowledgements to, of course, Rob Hobday, the CEO of AWA. Thank you so much for arranging this. And Mike Miglaccio, AWA Vice President, Lynn Bisha, thank you so much. You are the curator for AWA, great job. And Steve, thanks for arranging this and connecting me to AWA staff, which is really very helpful for me and for my students. I'll also acknowledge my students who are constantly working in these areas. Paul, Connor, Ashley, Logan, Rushi, and Gavin. They will be visiting AWA soon also. And I will acknowledge Theodore Leckman for his work on Apollo Guidance Computer that I referred to, and David Laws from Computer History Museum. I get a lot of information from his website and from his publications. So I'm very thankful to this communication between us and maybe future collaborations. So I'm really looking forward to that.
Please like and subscribe to this channel and press the bell icon to get new video updates.